This is Captain Ross. This is our Upgrade OUPV to Masters 100 Tons course, Ocean Currents. So the movement of ocean currents is one of the two primary causes of differences between dead reckoned and actual vessel positions, with wind being the other main factor. So as a refresher, dead reckoning is a technique used to estimate a vessel's position by projecting from a known location based on the vessel's course and speed over a period of time and does not account for current. So if we look, here's a basic dead reckoning course line. So at 12:30, we start from this known position. We're on a course of 090 and a speed of 15 knots. So we can project our position where it should be at 12:45, which if we're going for 15 minutes at 15 knots, we should cover 3.75 nautical miles. We should put us right here in this position at 12:45, and then this position at 1300. However, dead reckoning doesn't account for either the current's effect on your course or the wind's effect on your course. So if we can look at this position down here, or this diagram, you can see we're starting at position A. We desire to go to position B. However, there's a set, which is a direction, and a drift, which is a speed of current, pushing us this direction here. So the entire time we would run on this course, we're going to be set off in this direction. And you can see that the current's going to slow our speed down and push us in this diagram down. So if we want to get to B, we're going to have to drive a course from A to C, which is our course to steer and speed to run, in order to reach this position at B. If we just drove the course to steer directly from A to B and the speed to run, we were going to end up down here somewhere. So this is why current is important to know, for the most case, before you leave. At least have some idea of what the current's going to do to you. So advances in modern shipping speeds have minimized the effect of currents. Electronic navigation systems offer continuous course corrections, decreasing the necessity to account for currents prior to a voyage. So that's two things that help us out. So imagine being in a sailboat like with Columbus coming across. Obviously they didn't know exactly how the currents were going to affect them, but they had a pretty good idea, I imagine, and how much that would affect your speed and direction you were sailing, because you were at the mercy of the wind and you weren't going very fast. So now we have, modern ships go pretty fast, so they can kind of push through a lot of that current. And then electronic navigation systems, especially if you use a route to steer, it's going to correct for any deviation off your course from that current or wind. So we don't need to know and account for the current as much before we leave for a voyage in modern times, but it's still very helpful. Ocean current. So an ocean current is a continuous flow of seawater driven by wind, the Coriolis effect, waves, and differences in temperature and salinity. Depth contours, shorelines, and other currents affect the direction and strength. So basically, we have these ocean currents running for a couple different causes, which we'll go over a little bit more later. And depending on where you're at in the ocean, the depth contours, how close you are or far away you are from shorelines, the shape of the shorelines, and then other currents, tidal currents, those kind of things are going to affect the direction and strength of these ocean currents. So they mainly move horizontally, and the direction which the current moves is called the set, and the speed it moves is referred to as the drift. So they're influenced by several factors. Tides are a significant factor and are driven by the gravitational attraction of the sun and moon on the Earth's oceans. Tides generate currents in the oceans near shore and in bays along the coast. Tidal currents are unique in that they change in a regular pattern and can be predicted for future dates. If you remember from your OUPV course, we went over tides and how tides work and how they can be predicted, and using NOAA information to find out what the tidal influences should be on any area that you're operating on any date, any time. Those can be predicted, very far out in the future. Winds also drive currents that are at or near the ocean surface. These currents are generally measured in meters per second, or knots. We're going to use knots primarily. Winds drive currents near coastal areas on a localized scale, and in the open ocean on a global scale. So trade winds, large weather systems can blow across the ocean and cause pretty significant surface currents. And then on a local scale, if we have a couple days of a strong wind in the same direction, how you can see it blow, like it'll blow across a Chesapeake Bay, let's say, and if it's blown out the bay for a couple days on end, you'll notice the tides are a little bit lower than normal, and they don't quite get as high as they normally do. That's like a wind-driven event, and those currents can definitely affect your ability to maintain a steady course and speed, and you're going to have to account for those when you're operating your vessel. All right, another way that you have some ocean currents is the thermohaline circulation, and it arises from differences in water density. And water density stems from changes in the temperature and salinity throughout the various ocean regions. So these currents can be found at both deep and shallow depths and generally flow at a slower pace compared to tidal or surface currents. So they're not going to have as much of an effect on your operation of your vessel. A couple of different ocean currents. Atlantic ocean currents. These are caused by trade winds that set up a system of westerly flowing currents conforming generally with the areas of trade winds, separated by a weaker easterly flowing countercurrent. The North Equatorial Current, which originates in the northward of the Cape Verde Islands and flows almost due west at an average speed of about 7/10 of a knot. The South Equatorial Current starts off the west coast of Africa and flows in a generally westerly direction, average speed of about 6/10 of a knot. There's a north countercurrent to those that flows east near the doldrums, fed by the westward equatorial currents, especially the South Equatorial Current. Its extent and length vary with seasonal winds. Two that we're going to experience here in the U.S., especially on the East Coast, or exclusively on the East Coast, but the Labrador Current, which is cold current that flows southward off the coast of the Baffin Island through the Davis Strait along the coast of Labrador and Newfoundland to the Grand Banks. It carries with it large quantities of ice. So that's going to be, this northerly current that flows south. And then the Gulf Stream, which is the one that we're all most familiar with. And that flows basically from Florida northward along the U.S. coast and then northeastward towards Cape Hatteras and then curving east and becoming broader and slower. The tremendous volume of water that flows northward in the Gulf Stream can reach speeds from 2 to 4 knots. And you'll hear about that especially off Florida. If you're going to make it a transit from the Florida coast to the Bahamas, that Gulf Stream current will really affect you. You have to account for that when you're making that passage. If you're going to be sailing or motoring south along the East Coast, when you get into Florida, that Gulf Stream can get pretty close to the coast, and you want to account for that because it's going to push against you trying to go south and really reduce your speed, or may. If you're in a large motorboat, it's not going to, but if you're sailing, it definitely will. So ocean eddies and rings, these are circular currents ranging from 50 to 100 kilometers in diameter, and that separate from an ocean current. These eddies generate their own surface current patterns and contain either a warm or cold core. The flow around the core moves counterclockwise in cold core eddies and clockwise in warm core eddies. I hear about these eddies most often from fishermen targeting, tuna and mahi and those species, and they'll go out in the Gulf Stream and try to find these eddies because it pulls that Gulf Stream warm water kind of closer to shore, especially off the coast of like North Carolina, all the way to Maryland. Produces better fishing, so they look for those eddies. Stronger versions of these eddies are known as rings, which form when the meanders of the western boundary currents like the Gulf Stream pinch off. These rings act as independent circulatory systems of warm water and can last for several months. They are powerful enough to reverse surface current directions, reaching speeds up to 2 knots. All right, so you're going to navigate your inspected T-boat up to 100 tons. What are some tools that we can use to kind of help you determine how the current's going to affect your voyage? So the Coast Pilot is a great source for this. It's a series of nautical publications from NOAA covering a variety of important information for navigators and maritime businesses. Here's a sample or a picture of the cover of Coast Pilot 4, which covers the Atlantic coast, Cape Henry, Virginia to Key West, Florida, Cape Canaveral to Cape Hatteras, that there may be an expected outside the 10 fathom curve current off there. So I would read that information if I was going on a voyage through that area and get specific information on the current. I apologize, I've got this on my computer screen and I can't read what it says. The print's too small. Actually, I can see it here. So it appears that except during northerly and northeasterly winds, a current of about half a knot average velocity setting, or the direction, is northeastward with the something of the coast may be expected outside the 10 fathom curve between Cape Canaveral and Cape Hatteras. Farther offshore, the velocity of the northeastward flow increases as the axis of the Gulf Stream is approached. So this gives you some basic information on this current that's flowing in between Cape Canaveral and Cape Hatteras. The next information we're going to look for, or source, is the tidal current info for U.S. waters. The best way to do this is to visit NOAA's website, tidesandcurrents.noaa.gov /NOAA currents /. When you visit that web page, you'll come to the first page you come to looks like this, and it has these different states on there. So for this example, we're going to select Virginia. So we just go down here. If I was on my screen, if you can see my cursor there, and select Virginia. And then I'm going to select, let's say we'll use this Cape Henry light, 3.4 nautical miles northeast at a depth of 30 feet. It gives the exact latitude and longitude of that position, and it's a subordinate current station or tidal station. And this is what the graph looks like for April 29th to April 30th. And remember, this is a current graph, not a tidal graph. So we can see we've got a couple of times here: 6 a.m. on the 29th, 12 p.m. on the 29th, 6 p.m. on the 29th, 12 a.m. on the 30th, and so on. And here's a graph. This is 0, so there's slack or no current movement. This is our speed in knots. This is our ebb, so it's going to be below this 0 line, and this is our flood. It's going to be above it. So we can see here on the graph, we're going to have a current of about, it looks like about a little less than 2.5 knots. And so if I go over here to my time, I can see that at 4:34 a.m., I'm going to have a max ebb current of 2.33 knots. That's what that graph showed me there. I can look at this flood peak right here, 9:54 a.m. I'm going to have a flood peak of 9/10 of a knot. 12:31, I'm going to have a slack, which should be right here. And then at 4:12, I'm going to have a ebb at 2.76 knots. So anyways, we can check our different times and read what the current should be doing at those specific times in this area, which is 3.4 nautical miles northeast of Cape Henry Light at a depth of 30 feet. All right, so let's ask ourselves a couple questions about this. So what is the maximum current speed or drift for an ebb at Cape Henry Light? So if we look at the 29th for this period of time that we're looking at with this graph, we've got an ebb here of 2.33 knots, 2.76 knots, and then 2.18. So obviously our fastest current is going to be that 2.76. It occurs at 4:12 p.m. What is the slowest current speed for a flood? So we'll check our flood, slack ebb, slack flood. We got 9/10 of a knot. Slack ebb, slack flood, we got 2.18. So it's going to be 2.18. It's going to be our fastest, and 9/10 of a knot is going to be our slowest for a flood. And then what is a time difference between 9:54 a.m. max flood and the next slack? So let's look at 9:54. Here's our flood at 9/10 of a knot, and then the slack is at 12:31. So if we're taking 9:54 to 12:31, that is what, 2 hours and 37 minutes? That's our time. So that's the kind of information we're going to use from the NOAA's website to help us navigate in consideration of ocean currents or tidal currents. All right, this concludes our presentation on ocean currents.